is empirical and molecular formulas. With this standard, we are going to get to the end of our unit on the mole here, and we're going to kind of approach an end to the math that we're doing. The first thing that we're going to look at today is determining the difference between empirical and molecular formulas. We've dealt a lot with molecular formulas in the past. We haven't talked about empirical formulas yet. The second thing we're going to do after that is looking at how to calculate, using percent composition, the formula for specific compounds. So you will first calculate the empirical formula, and then you will use that to calculate the molecular formula. Now, molecular formulas are something that we are all familiar with, and it specifies exactly which compound you're using. So this is just the mixture of element symbols and our subscripts here telling us how many of each element that we have. NaCl, sodium, H2O, water, CO2, carbon dioxide, CH4, carbon tetrahydride. We've dealt with these before. What we are more unfamiliar with are empirical formulas. So while molecular formulas identify precisely what the compound is, empirical formulas specify the ratio of elements in a compound. Now, they can be a little bit confusing because they will look exactly like molecular formulas, but they are going to be a little bit more simplified. And here's what I mean by that. Let's say you had two different molecular formulas. You have CH2O and C2H4O2, like I have listed here. Okay. So those are two different molecular formulas, which means that they are two completely different compounds. And they're going to have different properties, different masses, because they're two different things. However, both of these will share an empirical formula of CH2O, which means that the ratio is always going to be 1 carbon for every 2 hydrogen for every 1 oxygen. Now, if you notice here, it's just the most simple form that we can get these two molecular formulas in while keeping whole numbers. So CH2O, right, we can't really divide this by 2 because you'd have C 1/2, O 1/2, and we can't have half of an atom. So we're trying to get this as simple as possible to be the empirical formula. So if we divide this by 1, CH2O, divide it by 1, it becomes CH2O, which is the empirical formula. Likewise, C2H4O2, if you divide that by 2, then it becomes this, CH2O, which is also, right, the same empirical formula. So essentially what you can do is you can take the empirical formula and it represents all the compounds that have the same ratio. So if we multiplied these by 3, right, and we had C3H6O3, that would be another different molecular formula, but it would still have the empirical formula of CH2O because the ratio remains the same, 1 carbon for every 2 hydrogen for every 1 oxygen. Now that might be a little confusing in regards to like a why would we care sort of thing, right? Like, Mr. Brester, what's the point of having a molecular formula and an empirical formula? And the reason that we do it is because of mathematical reasons when we're determining unknown compounds. Last week, when we looked at 7.3, I said when you have percent composition, sometimes we'll go in the reverse direction, where you'll have an unknown compound, where you get the percent composition data, and you have to identify exactly what the compound is, what the molecular formula is. So when we solve for the unknown, because we have the percent composition, it's essentially a ratio of the elements, right? Like, let's say we have 75% carbon, 25% hydrogen. 3/4 of that compound is carbon, and 1/4 is hydrogen. So you're again solving for set ratios for the empirical formula. So we solve for the empirical formula first, and then we solve for the molecular formula. And you see here I've highlighted ratios. So when I say you're solving for the ratio, I mean you are first solving for empirical formula. And here specifies ratio of elements in a compound. The empirical formula is that ratio, and it's super important that you keep that in mind when we get to the math that we're about to do. If you were given the percent composition data and you needed to calculate an empirical formula, here's how you would do it. And there's 4 steps here. You have percent to mass, mass to mole, divide by small, and multiply till whole. Now when I presented this in the past, I had said it was kind of like a rhyme, okay, and I wish there was some way to get it to stick in people's minds a little bit more. And I was like, oh man, I wish I had like a song about this. So last year when I was doing this, I said that exact thing. I was like, I wish there was a song about this so it would stick in people's heads. And one of my students stood up in the middle of class. And he's just like, Mr. Brester, bet. And I was like, what? I don't understand. And he didn't say anything else. He just kind of sat down, and nothing else happened for the rest of the day. And so then at midnight, I get a file download from him in an email, and it's this song, and he made an entire rap using this. So I will link that to you because I find it helpful for me to just listen to keep it in my head. So again, percent to mass, mass to mole, divide by small, multiply till whole. So those are the steps, and over to the right here, I've got a little more specified. So what you're going to do is percent to mass. You are given the percent composition data, and you convert that over to a mass that is in grams. Mass to mole. We convert that mass in grams now over to moles. And we know how to do that. We've been doing that in 7.1, 7.2. 3. Divide by small. This is the step where we are getting the ratio. So you divide by the smallest number of moles. So all the different mole amounts that you had in each element, you divide by the smallest number of moles amongst those. So this, right, dividing moles by other moles, gives you the ratio of how many of a certain atom do you have relative to one another. That step number 3, is where you get your empirical formula. Step number 4, multiply till whole. If the results aren't all whole numbers, multiply them until they are whole. And that will kind of be a little bit iffy. Sometimes you do number 4, sometimes you don't. And I'll show you when and where, because sometimes we do get whole numbers and sometimes we don't. Alright, we're going to try this out. Let's say we start off and we are given the percent composition data. We have 75% carbon and 25% hydrogen by mass, and that's what our compound is made up of. How do we figure out the empirical formula? Well, we just follow these 4 steps. Percent to mass, mass to mole, divide by small, and multiply till whole. So here's what I'm going to do. I'm going to do each element separately, just like we did for 7.3. So 75% of the compound is carbon, and 25% of the compound is hydrogen. We're ready for the first step, okay? Percent to mass. Now, I do not like doing any more math than I really have to, and I'm sure you all feel the same way. There's no point in like burdening yourself with extra math. So here's what I do. Any numbers that you use are fine as long as we keep the same percentages. Now, it just seems easy to me. If percents are out of 100, we might as well just say our compound, this because it's imaginary, right? We're just imagining a compound weight, because we have percents. It doesn't really matter what weight we use, so we can use any weight. This is just a ratio. Percents are out of 100. We might as well just keep the total mass 100 grams. So what that means you can do is you can literally just say 75%, well, that's 75 grams. 25%, well, that's just 25 grams of carbon and hydrogen. Here's why this works. 75 grams out of a total of 100 grams is still 75%. 25 grams out of 100 is still 25%. As long as the percentages, as long as those ratios work out just fine, then the math doesn't really matter. So I say it's just easiest to do a direct conversion. Whatever the percent is, that's how many grams you have, because we just take it out of 100. Seems easy to me. So we've got percent to mass. Our second step, mass to mole. So here's where our 7.1, 7.2 skills come in handy. We are just calculating how many moles we have. So here's what we do. 75 grams of carbon is what we have, and we're dividing that by 12.01 grams in every mole to calculate how many moles we have. I get 6.24 moles. Sync status. We okay? Okay, sorry, I'm fixing that because I have made 3 recordings of this video and the whiteboard has gone out on all of them. So I want to make sure that it's still synced up properly here. So I'm just going to go check in my other tab. Okay, it looks like it is. Sorry for that pause. Oops, wrong tab. I just don't want to have to make this for a 4th time. Okay, so we have 6.24 moles of carbon. If I go on to calculate the number of moles of hydrogen, I'm doing 25 grams divided by 1.008, which gives me 24.8 grams, moles of hydrogen. All right. Now, that's step 2. We've done percent to mass, mass to mole. Step 3, divide by small. Look at the 2 values of mole that we have here. Okay, and you'd look at all of them if you had more than 2, but we only have 2. We have carbon, we have hydrogen. Which one is smaller? You divide both of these values for mole by that amount, and this is what gets us our ratio. So the smallest here, right, is 6. There we go. Sorry, my screen was updating here. 6.24. So we're just going to divide by 6.24. And that will get us 1 carbon. If we divide this by 6.24, not exact, okay, but it gets us right around 4 hydrogen. Now, these values here, these are our ratios. So this is our empirical formula. 1 carbon and 4 hydrogen. It's important to get the mass of this, and this is what's called the empirical formula. Wait, I'm going to say this is EFW. You might see some books record this as empirical formula, and they don't have a weight, so it's just EF, and you might see some books describe it as EW, empirical weight. I'm going to just say EFW, best of both worlds. Okay. Oh, why? if we take the molar mass of this, 1 carbon, 4 hydrogen, add that up, it's 16.04 grams per mole. Okay, so we've got our empirical formula. We did what the problem asked. Now, there's another step to this, though, because not all the time are we going to be worried about just what is the empirical formula. We want to know what compound we have. Here's the next step. If you are ever asked for a compound, you have to have the molar mass. They have to give it to you. So, let's say your lab equipment, okay, tells you what the mass of the compound is that it gave you the percent composition of. And a lot of equipment can do that, and they'll actually just tell you what the compound is because it's smart enough to know that. But in this case, we'll pretend it isn't. So the compound has a molar mass of 16.04 grams per mole. Kind of funny in our case, because that's an exact match to what we just found, right? 16.04. What that means is our molecular formula is the exact same thing because it has that mass. So this, I'm going to circle in really bright colors, hopefully. Oh, I apologize, everybody. I don't know why this has been so difficult today. Just open it anyway, doesn't matter. Come on. Okay, I apologize again for the delay. It's, like I said, this is the fourth time I've recorded this video, and it just has not worked out. That's not what I wanted. I wanted the sizing to change. Because I feel like it's a little small. Okay. Here's what we're doing. This that I've circled right here, okay, in all these bright colors for you, that's our molecular formula. And guess what? It matches our empirical formula because it's the simplest that we can get this with whole numbers, right? If we divided it by 2 again, we would have 1/2 of a carbon atom, which can't happen. So these match up. The important thing is that the weight here for our empirical formula weight is the same as our molecular and molar mass, As long as those are the same, then you know you have the same compound. But let's say, just for a little extra math, that it wasn't the exact same. And instead, we have the same problem, but our equipment actually said the molar mass was 32.08. Here's what happens instead. It's not just as simple as saying, oh, it's the same thing. What you're going to do is you're going to take the molar mass that you are given, and you're going to divide it by the empirical formula weight. So we are going to take 32.08, because that's the mass that we were given, and we're going to divide it by the mass that we found the empirical formula to have. Now, this works out to 2. This number is important because you are going to multiply everything in the empirical formula by 2. So we have CH4, so carbon turns to C2, right? And H4 multiplied by 2, that's H8. Now, this compound is our molecular formula. And if you have some doubts about it, you could always check the mass, right? If the mass agrees with the mass of the compound that we were given, then it's the same thing. And if you tally up C2H8, right, carbon 24 for 2 of these, and hydrogen is 8, so 8 plus 24, that's 32. This is the same compound. So C2H8 is our molecular formula. I'm going to go through one more of these before ending this video. So this time, we have an unknown compound with 3 different elements: carbon, hydrogen, and nitrogen. So I am just going to, where's the clear function? Clear this. Alright, so carbon, one of our elements. Hydrogen, one of our elements. Nitrogen, one of our elements. Carbon is 74%. Hydrogen is 8 point, I want to make sure I get this right, 8.65. And nitrogen is 17.35? 17.35. Alright, so we need to remember our 4 steps, right? Percent to mass. Easy. Since the numbers don't matter, I'm just going to keep the ratio the same, and I'm going to do I'm going to do a direct conversion from percent to mass. So 74%, that's 74 grams of carbon. 8.65%, nah, that's 8.65 grams of hydrogen. 17.35% turns into 17.35 grams of nitrogen. Alright, percent to mass. Second step, mass to mole. Again, taking our molar masses for each element and figuring it out like this. So 74 grams divided by 12.01, that is 6.16 moles of carbon. Eight 0.65 divided by 1.008 grams per mole. That's 8.58 moles of hydrogen. And finally, with nitrogen, we have 17.35 grams of nitrogen divided by 14.007 grams per mole, which is going to give you 1.24 moles of nitrogen. Percent to mass done. Mass to moles done. Divide by small. Okay, so we have 6.16, 8.58, 1.24. The smallest out of those 3, 1.24. So everything is divided by 1.24 moles, which gives us 1. .58 divided by 1.24. This is going to give us 6.92. This should probably round to 7. Now I said we were going to talk about that 4th rule. My go-to is I say if it is more than 0.15, okay, if it's greater than 0.15, then you should probably round up. Then you should probably not round. If it's greater than 0.15, you shouldn't round, and you should multiply until whole. If it's smaller than the 0.15, like it is here, we have 0.08, then it's okay to round. And this one I think is 5 something. 6.16 divided by 1.24. Yes. 4.97, which should round to 5 carbons. Okay. Whew. There's all the math done. Our formula with 5 carbons, C5, H7, N, 1, we don't put a subscript. The mass of this is 81.113 grams per mole. I remember that number because I've done this 3 times. But you can just, simply add up the 5 carbons, the 7 hydrogens, the nitrogen, and you can get that same number for yourself. Now, we go to the important part. That number that I just gave you, that is the empirical formula weight. Let's see if that matches up with the molar mass that we're given. No. The molar mass is 162.23. Good, we're still recording. 162.23. Remember, we take that mass, molar mass, divided by our empirical formula weight, and we get a number. And that number, again, is about 2 in this case. So, I'm just going to multiply all of my subscripts here by 2 to get the molecular formula. So our molecular formula is C10H14N2. And that number, this formula is nicotine. And its mass is exactly what we were given. Again, you can look this up if you want. I'm just telling you to save some time on this video. Okay? But if you add up the mass of 10 carbons plus 14 hydrogens plus 2 nitrogens, you get the same mass, which agrees with our molar mass. So that's how we know that we are correct, that this is our molecular formula. And this is nicotine, okay, in case you're wanting a name for this. So that's how we would solve that problem. What compound is this? Nicotine. Okay, so I know the math is a little bit lengthy, just like in 7.3, but again, follow these 4 steps, okay, percent to mass, mass to mole, divide by small, multiply till whole, and you should have no issue going through, okay? I think everything will be fine. It's just long to do, so make sure you double check your work, because it's easy to kind of get in a routine and not check yourself, and then you'll make mistakes, but the math itself is fairly simple. Alright, that'll wrap up everything for 7.4. So let me know if you have any comments or questions, and I'll see you all later.